Okay guys, week 11. This week we are going to discuss a topic on mobile solutions for deep learning because, well, deep learning is everywhere. I always tell you this. And I've got an undergraduate course where I teach embedded systems, and this is the graduate version of it, in deep learning included. And I always tell everybody, in a couple of years, not decades, in a couple of years, guys, embedded systems will be all over our body, in our shoes, in our coats. Actually, there are already some shoes with some embedded systems, but all those embedded systems will include deep learning devices, which are able to do very complex decisions based on the senses they have. So deep learning, embedded deep learning, will be on mobile devices very soon. So this week I wanted to I want to discuss a little bit about the mobile solutions, because in the literature there are specific solutions for mobile systems regarding deep learning networks. Let's continue and delve into the discussion. Okay, the reality is we still don't have efficient DNN solutions for mobile systems. Deep neural networks do not very efficiently run on our mobile devices yet. You may have the best mobile phone, iPhone 11 or 12, I don't know which one, or Samsung's best, I don't know. You may have the best one. If you try to do any kind of deep learning, it takes time, guys. There are some apps that does deep learning, but they do it on the server. So still, the companies does not rely on the processor of the mobile device, because it's very hard for the mobile device to run the DNN. We have seen many methods to make the deep neural networks more efficient on these devices, like quantization or factorization of convolution, or binary neural networks. They are all solutions. However, maybe if there was a solution specific for mobile systems, which addresses the needs of the mobile systems, that would have been better, right? Actually, there are some research groups, especially Google, because Google is producing a cell phone as well. You know, Google has a cell phone. They are selling a cell phone of their own. They have the iPhone of their own. That's why they've got deep learning studies specifically on this field as well. DNNs for mobile devices, which is called the MobileNets. Actually, MobileNets. If you click on this link, if you go to the website, it's an original paper by Google guys. These are very famous guys from Google, and in their paper they propose a new network which is called the MobileNets. Actually, this is a classification network. The idea inside can be applied to any type of network, segmentation or fully connected, whatever. You can implement it on any system, but they've got a new idea to make it more simpler. They call it MobileNets because they apply it to a classification system which could run better on a mobile system. So I get to my slides. So the idea was, as usual, to make a smaller network size, to make low computation cost, to make low latency. Latency is the amount of time that you spend from the input to the output. If the network is deeper, it takes longer time to get the output, but if it's shorter, it will take shorter time to reach the output, right? And still high accuracy, because that's the beauty of the deep learning. Deep learning provides very high accuracy. If you lose that accuracy, there's no sense in using deep learning, whatever you are using. And smaller network size is also important for training as well, guys. If you make it smaller, yes, latency will be lower, but you will train the system more fast. Because whatever you do, when you just put your system in an embedded device, you will need to train it, and in time maybe you will not need to do the training on the device itself, which is quite difficult. So if it is smaller, its training is faster, it's easier to deploy on mobile systems, because imagine you have AlexNet or VGG, which is originally 150 megabytes. Well, you can download it, but constantly changing this or downloading such a network would be difficult. If you make it shorter, if you make this network shorter, if you make the network lightweight, well, it will be easy to deploy. Thus, it will be easy to update, which is almost always necessary. you train a network, then you will try to change the network and you will have to update it. So for mobile systems, these properties, smaller network size, computation cost, lower computation cost, low latency, and of course high accuracy are very important titles. Okay, so what did MobileNets do? Actually, what MobileNets did was nothing but co-design, guys. You have seen co-design, but this is another approach to co-design. So actually, this week when we visit MobileNets, actually we are doing another kind of another approach to co-design. We have covered many co-design techniques. So far we have talked about architectural compression, like layer design, pruning, flattening. In a couple of slides I'm going to cover these, the evolution of co-design in more detail. Or we have worked on not on the architecture but the weights. We have quantized the weights or activations by using post-training methods or training-aware quantization methods. Or we have done compression using weight coding with or without quantization. So we have seen some co-design techniques. We have discussed them. MobileNets is another type of co-design. So where is it in the co-design world? Let's try to understand. So this is a very simple. It's a very simple list of co-design techniques, which is like a picture of the co-design evolution. And because people have worked on co-designing deep neural networks for making them more efficient on embedded systems, they have been working on this for a while. Within the last 5 years, by the way, guys, you know this is very, very new. They started with a couple of techniques, and in time, these techniques got better and better and more complex and more advanced. So before we get to what we've done in MobileNets, actually it is this one. I've selected some titles. Actually, there are a lot of co-design techniques which we may cover, but these are some titles which I believe will clearly represent the co-design evolution that we have witnessed within the 5 years. Okay, so architectural comparison techniques in deep neural networks co-design could be listed in this manner. We start with pruning. We've always talked about pruning, but I don't remember us talking about what exactly pruning is. Actually, pruning comes from a concept which is related to real neural networks, the neural networks in our brains. So there's something called synaptic pruning in the human brain, guys. In the human brain, you might have heard of these if you're interested in neural networks. If you haven't heard of these, I'm trying to explain. In your neural system, you have these neural cells, guys. In each neural cell, you have an axon, which is like the edge of the tail, and you have the dendrites, which is these like tails or tentacles coming out of the neural cell, guys. And each axon, this edge of this long tail, touches one or more of the dendrites of the main cell body. That's how the electrical signals are transferred in our body. What is synaptic pruning? So this is called the synapse, where this axon touches the dendrites. That point is called synapse because that synapse is the exact point of the electrical current transmission. So it's very important for us. So when you're born, nearly every axon is touching every dendrite in your brain. So this one is touching this. Everybody is touching everybody. So you've got like 50 trillion synapses. In time, this number increases, guys. So maybe I told you wrong. When you're born, not every one of them are touching. Within the first 1 year, the first year of as a baby, these guys touch every one of them. So your synapses, the number of synapses, make a peak. Then in time, you lose some of the synapses you don't use. This is called pruning. It's like getting rid of some of the connections. It looks like dropouts, but it's not exactly dropouts because dropout is something random, but your mechanism in your brain and your neural system does it cleverly. It just doesn't use the synapses which are not useful. You can do this in neural networks as well. there's an application for this in neural networks. Well, when you first design them, neural networks, artificial neural networks, looks like this. But when you do some pruning, they will look like this because some of the transmissions you don't need. How do you know you don't need them? Well, if they don't fire many activations, you may cut them. Imagine you have a pre-trained network, everybody is connected to everybody. If there are dropouts, not everybody is connected, but dropout is another story. Everybody is connected to everybody in the end. Then you got the training set or some test set. You apply every image and realize that some of the nodes are not firing at all. You are not using them. Just cut them. Prune them. That's called pruning. In that case, your connections will be sparse. And you will have a sparse network, which will make your system lightweight, which will make the number of multiplications much lower. This is the very basic technique we apply in DNNs co-design, because it's in our brain as well. And when you do this, actually you can apply it to these weights, because setting individual weights in the weight matrix to 0 is actually weight pruning. This will lower the number of multiplications you do and the number of space you require for your system. So this is pruning, guys. This is a very basic one. If you don't fire, just kill it. That's what your brain does. Do. So that's a very nice technique. But you know that in time, these networks have advanced also architecturally. Not only physiologically like this, architecturally as well. Just like evenly spaced downsampling, as known as pooling. Let's continue.